Okay, the recording is progress. So welcome everyone to this morning SpaceGeekSpeak session. SpaceGeekSpeak is the informal gathering every Saturday morning at 8:30 Houston time. And we sometimes have speakers, like today we have Randii speaking about the future of US robotics, planetary exploration. On other times, it's an informal discussion on everything, anything and everything related to space exploration, engineering, and anything in between. Today, we have a unique opportunity to hear Dr. Wessen presenting about future of US robotic planetary exploration. Dr. Wessen has been an employee of the California Institute of Technology's JPL since 1984. He's currently the A-team lead study architect for JPL's Innovation Foundry. Previously, Dr. Wessen was the telecommunications and mission systems manager for the Mars program, the supervisor for the science systems engineering group, manager of the Cassini science planning and operations element, the Galileo deputy sequence team chief, and the Voyager science sequence coordinator for the Uranus and Neptune encounters. He received his bachelor's of science in both physics and astronomy from Stony Brook University, master's of science in astronautics from University of Southern California, and doctorate in operations research from the University of South Wales, United Kingdom. Dr. Wessen has written numerous papers on market-based systems as applied to space exploration allocation problems, and co-authored both the Neptune, the planet, rings, and satellites, and the Planetary Ring Systems books. Dr. Wessen was the recipient of NASA's Exceptional Service Medal for his contributions to the Voyager to Neptune encounter and has 11 NASA Group Achievement Awards. He was awarded JPL's highest honor, the Award for Excellence, for his outstanding initiative, dedication, and contagious enthusiasm for his public outreach efforts. Dr. Wessen is also a fellow of both the Royal Astronomical Society and the British Interplanetary Society, and an associate fellow of the AIAA. Dr. Wessen, welcome. And logistics, as far as the questions throughout his presentation, please hold on until in between the slides and when you're asked for if there's any questions. Otherwise, you're welcome to place it in chat, and then those questions will be answered in the order they were received. Thank you, and we are eager to listen.
Thank you, Svetlana. Morning, everybody. The way I'm going to handle this talk is I'm going to first give a little introduction of where the Jet Propulsion Laboratory came from, and then I'm going to march through the solar system, Earth, Mars, solar system, universe, talking about missions that are in operations or currently in the future. I can't go too far into the future because after about 30 years or so, it starts to get really science fiction-y. But what I'd really like to do is kind of give you an overview of really how we are leading the effort of robotic exploration. So basically, we do the robotic ambassadors to these worlds, and then it's followed by human endeavors. So let's just start. So I'm going to share my screen. Share, hopefully you can see this. I'm going to pull up my presentation. Can you guys see that? Hopefully that's a yes.
Not yet.
And again, feel free if you have any questions just to shout them out. Okay, so where does this whole thing start? And I want to talk about the Jet Propulsion Laboratory.
Hold on a second, Randii.
We don't see anything.
Yeah, we don't see your screen. Can you try it again?
I think you have to be made a co-host so that you have access to share screen, and then
he does. He has a share screen access.
So I clicked on entire screen and I said share. Oh, now it's not letting me do entire. How about? Wow. I clicked on entire share, but the share button does not light up. Any idea?
I have selected that the multiple participants can share. Yes, and
Let's see. How about now? Can you see my screen?
no, we can see you at the moment.
I'm not sure what to do. I've clicked on the share button. I clicked, it's on entire screen. I click on the window. The share button lights up. I select share.
You have to be authorized to share.
And he is, Zafar.
Please grant browser access to the screen recording.
I think it's you need to share, do that, because I don't have that on my side.
Browser access.
I've never seen that before.
Neither have I.
Okay, now I see your, looks like.
Can you see the Caltech logo?
Not a Caltech logo, but screen broadcast.
Huh.
Are you recording your screen?
No. I see your window here. You're viewing.
That appears to be David Hansen's screen.
Okay.
Dave, are you doing something on your phone?
There.
Yeah.
Okay. So now you should be seeing the Caltech logo.
Yes.
Yes?
Yes.
Yes, we do. Mm-hmm.
Okay. So let me start again. So Caltech started in 1891, and it was an academic institution, and it was doing a number of areas of research. One of the areas was in astronautics. And this slide is referred to as our nativity scene. A small group of individuals, led by Theodor von Karman, professor of aeronautics at Caltech, was doing rocket research on Caltech campus. And the administration was really worried that these individuals were going to get some students killed. So they said, look, go up into the arroyo about 5 miles north of Caltech and do your rocket research there. So here these individuals are in the arroyo, and you can see their little rocket stand that they were doing rocket tests. But the question we always get asked is, why are we called the Jet Propulsion Laboratory when we do deep space robotics? And that's because this picture was taken in 1936. You then had World War II. The military realized it, said, hey, you know, if you could get airplanes to take off on half a runway, that would require your opponent to drop 2 bombs per runway, because if they only drop 1 bomb, you still would have half a runway to take off on. So they came to JPL and said, well, it wasn't JPL at the time, they came to Caltech and said, hey, could you build rocket bottles that you could put on the wings of airplanes to take off in a quicker, shorter runway? And that looked like this.
We are currently seeing your JPL home screen, not a photo.
You're not seeing any images.
We're seeing the 5 images on the JPL Space home screen.
No, that's not what I want you to see. Yeah. So you're seeing this thing that says JPL Space with the 5 images on it.
Yeah, with Scopus and the other
Scopus.
images.
Mm-hmm.
That's not what I want you to see, though. Got ahead. I am really at a loss. I click on share. I usually in the past have done the entire screen and say share, but you can't see what I'm showing.
Well, now I think you stopped sharing, right? At the moment.
I did.
Okay.
Yep. Google Chrome will not be able to record the contents of your screen until it is quit.
Can you use
Can we
instead
try?
of Google Chrome, can you use Firefox? Maybe it's something.
You think it's a Firefox issue?
No, I think it may be a Chrome issue.
All right,
They-
tell you what, I'm going to leave and come back in Firefox.
Okay.
Okay.
All right, I'll be right back. The individual is being called a suicide squad. Excuse me?
Okay. It was, sorry, I restarted recording.
Okay. So this is where they worked about 5 miles north of JPL and did rocket tests. And as I said, they were working on putting rocket bottles on the wings of planes. And the trick is you had to ignite it in such a way that you had a controlled burn so that they did not explode and take off the wings. But as you can see here, here is one of their tests, 1941, where they put rockets on the wings of the plane, and you can see how quickly it takes off. That is where the jet in the Jet Propulsion Laboratory came from. So the military wanted us to do more of these things in mass production, which we don't really do. But when they signed the contract with us, they said, "What is the name of your company?" And we said, "We're not a company, we're Caltech." And they said, "Well, you have to put a name in for what you guys are called." So rather than being the Rocket Propulsion Laboratory, which they thought was too much science fiction, they said, "Let's call ourselves the Jet Propulsion Laboratory, a division of Caltech." So we became JPL in 1944, a division of Caltech. This is what JPL looked like in the early 40s. It was about 156 acres, as I said, north of Pasadena, kind of between Pasadena and La Cañada, but it was just basically a barren field with just a few barracks. Well, NASA was created in 1958, and NASA wanted JPL, but Caltech didn't want to give it up. So NASA pays Caltech to run JPL. So of the 10 NASA field centers, we're the only one that's considered a contractor because we're Caltech employees. We're not civil service. So that's where we started. Our first major success was really with Explorer 1. And I love this picture. On the left is Bill Pickering, who's the director of the laboratory at the time. The individual on the right is Werner von Braun, who was from Operation Paperclip in Germany all the way through the Apollo program. Helped design basically the rocket program for NASA. The guy in the middle is Jimmy. And we called up Jimmy, who was working at the University of Iowa, and said, "Jimmy, for our Explorer 1 spacecraft, we have a little bit of room. If you could put anything in there, what would you put in the nose of this spacecraft?" And Jimmy said, "I'd put a Geiger counter in there." Well, we launched Explorer 1, and Jimmy's Geiger counter went off, and it measured belts of radiation. Jimmy's full name is James Van Allen, and was basically the first scientific discovery in space. The Van Allen radiation belts named after him. So you got Pickering, Van Allen, von Braun, and that's kind of where we started. This is the laboratory today. Now, I can't say today because of COVID, but we were up to over 6,000 employees, and it's basically its own city there. In addition to the laboratory, in order to communicate with deep space spacecraft, we run the Deep Space Network. This is a collection of antennas that are located about 120 degrees around the Earth. So we have a number of dishes in Goldstone, California, outside of Madrid, Spain, and outside Canberra. And these are precision devices. So even though this thing is 70 meters across, something like 256 feet across, I usually use Neptune as a yardstick. When the Voyager spacecraft was at Neptune, high power on our transmitter was about 23 watts of power. That's the power to run the light bulb in your refrigerator. Well, when you're 3 billion miles out at Neptune, the signal strength that these 70-meter dishes were picking up was roughly 1/100000th of 1/10000000th of 1 watt. And now we're about 4 times further out. So these are really precision devices, and we manage this network too. Well, we have to start anywhere. The first trick is getting off the Earth. So you guys have all seen these things. This is actual footage of a rocket cam looking down the length of a launch vehicle as we leave. And as you know, this is not sped up. This is not fake. This is not animation. This is the runtime. And it just talks about really what it takes to leave the Earth. And what I think of in terms of cost, without correcting for real year dollars, the Saturn V was about $1 million per pound to orbit. The shuttle was about $100,000 per pound. Today's rockets are about $10,000 per pound. SpaceX is starting at $5,000 per pound, and SpaceX would like to get to $100 per pound. So you can see that space is really opening up. Matter of fact, I tell my kids that they're the last generations of human beings to be able to say, quote, I remember looking up at the moon and remembering when there were no city lights were on it. But as you can tell, it does not take long to get to orbit. I mean, what is it, 8 minutes? It's 350 kilometers up. It really doesn't take long, but that's where the journey starts. Well, this is an animation, and it just only has a few spacecraft in there. But if you think about it, you've got all your commercial networks, stuff from different nations, but the ones that we're curious about are the ones that are doing science. Now, usually it's the Goddard Space Flight Center that does Earth science, but 30% of our funding is also Earth science. So the distinction between what the Goddard Space Flight Center does and what we do at the Jet Propulsion Laboratory, Goddard does weather, JPL does climate. We do the long-term evolution of weather. And we can do some pretty entertaining things. So one of the experiments we did was a mission called GRACE, Gravity Recovery and Climate Explorer. And this was kind of done as an experiment. Could you take 2 spacecraft, separate them by 150 kilometers in low Earth orbit, and then put a radio and now a laser link between the two and measure how the range between the spacecraft change to submicron? And by doing that, you can actually make gravity field maps of how much mass is below each of the spacecraft. And if you look at the bottom right, you can see what these gravity field maps look like. Red is more mass, blue is less mass. And so we can see things like bulges in the ocean due to El Nino. We can see glaciers melting and the land rebounding back up as there's less water ice to hold that part of the land mass down. And it's basically a way to give the planet an MRI. Any questions? Are you guys okay? All right.
Looks good. I love it.
Okay, so we have this for Earth science. What we're also able to do is make what we call interferograms using radar, where this is California. And what we've done is we made an interferogram between radar image before and after an earthquake, and that's what gives you those butterfly patterns. The same color is the same amount of deformation so that you can see how quakes deform the land after a quake. And we're hoping by doing this and getting a data set of what the land was before and after a quake, we can get an idea of modeling how quakes deform the land so that we can get a better idea of how to predict quakes. Now, this is the only thing that probably can be deemed political, but it's not. Basically, I'm just showing you data. This is data of the amount of CO2 in Earth's atmosphere from about 400,000 years ago to today. And when people say, you know, weather is, well, climate is really cyclical, yeah, you can see there's about a 50,000 year cycle where we go from max to min. But you'll notice after 1950, you have this really steep rise. This is data. Anybody that says there is not climate change have to explain why we have this peak that's getting to over 400 parts per million of CO2 in the atmosphere. And what I would say, just as to give you a sense, 1950 was kind of right after World War II. There was about 2 billion people on the planet. You're now at 8.5 billion people on the planet. And after World War II, the world basically industrialized, putting more CO2 in the atmosphere. So I tell you, it's really anthropomorphic. It's really due to people, but you could say it's not, or there's no climate change. You still have to be able to explain that peak. To see this visually, this is the amount of CO2 in the atmosphere. When you see blue, you're about 370 parts per million. Red goes to 410. You could see the years going by there. I should say that the months are just clicking down, and you'll notice that it's getting redder and redder. And we need to do something about it. And since we're all engineers, you know the answer is not to solve the symptom, it's to solve the problem. So CO2 sequestration, getting carbon out of the atmosphere, is not the answer. You have to stop putting more CO2 into the atmosphere. All right, now I'm going to get to the stuff that you're more interested in. This is going to the planets. We're going to start at Mars because there's a lot of stuff going on Mars. But Mars has really been very schizophrenic. First, they thought it was dead, then they thought it was alive, then they thought it was dead. We're really trying to understand what's going on with Mars. You can see Mars is about half the size of Earth. We have this huge Valles Marineris. This is a Grand Canyon that would stretch across the United States. You can just barely see 2 of the 3 shield volcanoes. These are the small volcanoes. They're dead, but each is about the size of Mount Everest. The really big one, Olympus Mons, is 3 times the size of Everest with a footprint about the size of Texas. So that would have been a lot of fun to watch that thing erupt. When we look at Mars, we can see 3 different places where you have a source of potential water. The left image shows you a dried riverbed, which has all the characteristics of a dried old river channel. That's when they meander. On the right, you can see the polar caps, which are dry ice and water ice. The middle, your eyes are not deceiving you. This is water vapor in the atmosphere. So there actually is water around. So here's a Mercator projection of where we've landed, and it's not just us. We have European landers on here too. You can see by the equators, white is really high, so you have the 3 white tips from the shield volcanoes, and there's Olympus Mons about 20 degrees north of the equator. It's color-coded, so yellow is a reference level. Orange to red is highlands, so you can see the whole southern hemisphere is, excuse me, is this highland plateau, and it's heavily cratered, except for this massive crater in the south. The whole northern hemisphere, though, you'll notice, is blue and relatively devoid of earthquakes. And, we have to explain that in terms of the history of Mars. You could say that Mars was impacted from the southern hemisphere, but now you have to explain why the asymmetry. Why was the northern hemisphere impacts different from the southern hemisphere? But you'll see that the northern hemisphere is lower down and smooth, which has led a number of people to say that Mars was hit by something in its early past, and that was the lowlands, and that Mars 3.5 billion years ago had a North Polar Sea, and that maybe water ran through Valles Marineris out into the North Seas. So the question was ever long-standing water on the surface of Mars? And when I say long-standing, if we know you have ice, if you get hit by something and it liquefies the ice into water and it floods, it can give you river channels, but then it would just boil off. If it's there for a short term, it's not there to evolve life. If it was sitting there for millions or billions of years, now you can have something that's available for life. So we want long-term standing water on Mars. And that's what the whole Follow the Water campaign was. Well, one of the interesting things we saw from Mars Reconnaissance Orbiter is, this is an MRO photo. See those black dots? We find them all over the moon, and we find them all over Mars, and we're going, what the heck are these things? So we brought in the HiRISE instrument to look really close at these things, and we saw this. These are what we call skylights. You can see the size, 310 and 180 meters respectively, left to right. These are what we believe skylights are, is that you have these lava flows that get encrusted over as the top cools, but lava still flows through these things, making tunnels. And then the ceiling caves in to form a skylight. These are what we really like to explore. And the interesting part is not necessarily the tunnel itself, because that'll record the last lava flow to dry through that tunnel. What you really want to do is you want to go through the sidewalls from the surface, looking at the stratification of the walls as you go through that. One idea is we're working on these little gecko kind of things that can basically, using the same action that geckos do with microscopic feet, to stick to the walls and climb up. But the one we really like is a thing called dual axle. Picture a four-wheeled cart that would drive to the edge of a skylight. It would lock its back wheels and then dislocate its front wheels. And that's on a tether, and the axle and its two front wheels would drive down on a cable down into the skylight, looking something like this. This was a mission we actually proposed for Discovery called Moon Diver. You can't see the rover. It would be at the side of the lava tube, and this thing would just run down, looking at the stratification of the walls of that skylight, because with each flow of lava through it, it would add another layer. So it would capture basically the history of the solar activity in the stratified walls of this skylight. So we'd like to propose those not only for the moon, but eventually going to Mars. But right now we have a number of rovers driving around Mars. You've got the Curiosity rover, which is 9 years on the surface. So this was looking for organic compounds. And it landed in a crater that had a central peak the size of Mount Rainier. And it, from its landing zone at the 2 o'clock position, it's been traveling in the 7 o'clock position, and now it's going up the walls, looking at the evolution of what's going on, because the stratification of Mount Sharp is a recorded history of the climate on Mars. One thing that people need to be careful about when you look at images that we return from these vehicles, we find that when you have 7/1000ths of an atmosphere of CO2 and you're 1.5 astronomical units away from the sun, it's hard to look at the rocks and understand what minerals you're looking at. So we do this thing called white balancing, where we take an image of Mars and then we change the color balance to be what would Mars look like if it had a light blue sky and you're 1 AU away from the sun. This is a white balance picture, and that's why you see a light blue sky. Mars does not have a light blue sky, but it's easier for the geologists to look at the rocks and identify what minerals are embedded in them. The idea was that Mars had a molten core and it had a magnetic field, and then as it cooled, the magnetic field would actually collapse. So now the solar wind particles, the protons, electrons, hit the atmosphere, knocking off atmospheric gases. As the atmospheric pressure falls, the pressure gets so low at one point, the water on the surface just boils off. And the question is, was that really the process? So we're using InSight to try to measure how that, is that really going on still today at Mars, because there still is a little bit of an atmosphere on Mars. We then have what we landed in 2018, a thing called InSight. It had a heat probe that wasn't able to penetrate down, but we did have a seismometer that we placed on the surface, and we had to put a windshield over it because this was so sensitive. But let me give you an idea how sensitive the seismometer is. You don't need to make a good seismometer for Earth, because Earth is always shaking. We have quakes all the time. They're usually very low magnitude quakes, but it's still shaking all the time. This seismometer that we built for InSight, that I should say that the French did, that we helped work on, is so sensitive that when they were assembling the prototype of this seismometer in Boulder, Colorado, you had to filter the data coming out of the seismometer, but it was so sensitive that it could pick up vibrations from waves hitting both coasts, from the Atlantic and Pacific Ocean. And to date, we've measured over 500 quakes on Mars. Most of them are less than magnitude 3, but Mars still is quaking, and data indicates that the core of Mars has not completely solidified. It still has a liquid core. For the Perseverance rover that we just landed, we landed in the Jezero crater. And the reason why we wanted to land here is we're going to focus in that area right there in this blow up. And you could see it really looks like a dried up river delta. And that means there's sediments, that means there's clays. Clays are great for preserving organics. That's the region that we really want to explore. So that's the area that Perseverance is in. For those who just want to relive it, this is how we landed on there. We came in 13,000 miles an hour. We lose the cruise stage after we've got the right entry angle. This is powered descent, where you use the thrusters to clock the spacecraft. So you're rotating, and that's kind of how you steer. Once there, you blow up the hypersonic parachute. You then let loose the heat shield, because you no longer need that. With the heat shield gone, it exposes the vehicle itself. And you'll see that here. So there goes the heat shield. So there you have the rover in the wind. There goes the heat shield. You now drop the whole combination of the rover with the back, with the jetpack. This is called the sky crane concept. It has a map of where it's trying to park the rover, and it's taking images all the time and comparing where it wants to go to where it thinks it is to land it. We then let it down on a bridle. There are 4 cables. 3 are the load. 1 is the power, and it just releases it, and then that just goes, burns to depletion and crashes. Piece of cake, but there's a reason why we call that 7 minutes of terror. Well, one of the technology things, because this was not the main objective, was to drop a helicopter on the surface. This is a 2-kilogram helicopter, and it is just a demo. We like to think of it a lot like Sojourner, which was a demo rover that we landed in 1997. You've got 2 counter-rotating blades, and we wanted to demonstrate heavier than air flight on another world. It only has a camera on it. It's usually used for navigation, so it is imaging the ground below it as it tries to navigate to its position. It was designed to have 5 flights. And now here it is on the ground. And if we look right there, we've now had 12 flights of Ingenuity, which is the name of the helicopter. We are using this as a scout to help the rover decide where the interesting landforms are and which are the safe paths to traverse through. And even as this thing is still in an operational phase, we're now looking at designing a 30-kilogram helicopter, because there are clearly a number of fun places on Mars you can't get to with a rover that you could with a helicopter. Now, what the rover's primary mission is to do this. We want to do the first leg of a sample return. And the way this is envisioned work, Perseverance would go through the Jezero crater, look for interesting rock forms. It would not drill, but it's taking a core sample out, take the core sample, pick it up, basically ingest the core sample inside the vehicle. That's the turntable, then rotates that underneath where there's a second arm. The second arm would take the sample and then pull it out and then move it into basically a tube that has full of instrumentation to assess what we have in the tube. So it'll measure how much material is there, it'll seal it, and it'll image each step and then move it to storage. And as you may know, the first sample came up empty, and that's because the soil dynamics on Mars is different than Earth, and the stuff we believe just turned into powder. So as we pulled it out, it just fell apart. There was basically no material strength to it. So we need to figure out how to collect samples, which probably means having to limit ourselves to much more denser bedrock to pull these samples out of rather than the clays. That's the first part. The second part would be to have, and the Europeans are providing us this, a fetch rover and a lander that we would collect the 30 some odd samples that Perseverance collects, bring it back, the fetch rover bring it back to this lander that would put it in a MAV, a Mars Ascent Vehicle, that the US is going to design. That would put it into orbit. The white circle at the 7 o'clock position, that is the sample canister with the 30 some odd tubes. You'd have a European orbiter that would collect the sample and then bring it back. So it'd be the first sample return from Mars. But the thing we're really interested about is subsurface. If you had a balance beam, and on one side of the balance beam, you put all life that you know of on Earth on it. So on this left side is balance beam. From the air, you take birds, bugs, and bees. From the ground, you take cows, pigs, trees, grass, shrubbery. From the oceans, plankton, coral, crabbies, that stuff, and you put all that stuff on the left side of this balance beam, you'd have a certain amount of mass associated with those life forms. If on the right side on Earth, you now drill down into the bedrock and you pulled out the single cell lithotrophs, the rock lovers, and you put them on the right side would have more mass. So there's more energy, more life energy tied up with lithotrophs than everything else combined on the Earth. So you can envision that Mars, if it was wet and had long-standing water for a period of time, and it could evolve life as the atmosphere pressure fell, that might be an evolution pressure for things to go subsurface. So could there be lithotrophs on Mars? That's really what we're looking for now. All right, let's move on to the outer planets. We have Juno, which was designed to look at the inside of Jupiter. So looking at fields and particles and infrared, it was able to do things like this. This is a movie we made. So what we've done is we've animated Jupiter, and then we've added the structure that we're seeing below the clouds due to its instrumentation. So we can see these vortices at the North Polar region going on, because we're really trying to understand the dynamics of the giant planets. Because one of the embarrassing things in my business is we don't know how planets form. Some people say you have an accretion disk and it starts with particles accreting together, getting bigger and bigger. And as it gets bigger, it's got more mass. So it's got more gravitational field, which sucks in an atmosphere. So that says you start with a core and then you build up an atmosphere. Other people say, no, no, no. In your accretion disk, you've got these gas pockets that trap dust particles and that capture these particles to build up a core. So that says you start with an atmosphere and then you build up a core. The idea that we don't understand how planets form is really kind of depressing. But what we're doing is we're trying to query these outer planets with entry probes and things that can go through the atmosphere to look at the structure beneath. Now, in the Jupiter system, one of the wild things is, we used to think that moons and the outer solar system was kind of boring and geologically dead. It's not the case. There's a moon called Europa, and we're designing a mission called Europa Clipper that'll launch in 2024 to actually query what Europa is all about. And what we think it is this. We believe that you have an ice cap that is 5 to 10, maybe 15 kilometers thick, with a liquid water ocean underneath. We think the amount of liquid water underneath that ice cap is equal to twice the volume of all the liquid water on Earth. So these are huge amounts of water. We think there might be hydrothermal vents on the bottom. And we know Enceladus on Saturn is venting continuously. We think Europa on Jupiter may be venting also, but not nearly as fast. So Europa Clipper is going to be designed to actually query what's going on Europa and looking below the surface with a radar. The three ingredients for life, we believe, life as we know it, is you need liquid water, you need an energy source, and you need organics, carbon and hydrogen. Well, we know there's liquid water there. If it's liquid, it needs an energy source to keep it in the liquid state. And organics, carbon and hydrogens are everywhere. So when we ask the science community, where would you like to explore? If you could explore the ocean And we gave them three choices. You could run along the bottom with the hydrothermal vents, you could swim in the middle, or the ice-water interface. They said the ice-water interface is the most interesting because you'd have convection cells bring material from the bottom up to the surface, and Jupiter's radiation would fry the surface, and you'd get these you'd get these different chemistry going on the surface that would fall in through crevasses. So what we started to do is we started to work on this. Drills, or you already have paths to the liquid water ocean. Those would be the vents themselves. So for the vents, we're trying this thing. This is called EELS, for Exobiology Extent Life Surveyor. What you do is you would land near one of these plumes, and then you would tether out a cable, which has this snake-like thing that's got these counter-rotating segments that would propel itself. It would then lock at the side of a crevasse and stick its head in, which has a lot of instrumentation on it, pressure sensors, composition, so on. And then once it does that, it would then actually drive down one of these vents. And we're actually building these today. They're not as capable as we need yet, but we're starting on building those. We also, this is not funded yet, we would like to actually land on Europa. It would probably only last 3 weeks, but you'd actually get in situ measurements of what's going on the surface with one of these things. One of the fun things is we partnered with a company in San Francisco called Autodesk, which uses a lot of AI and self-learning software. We said, you know, we know how to build landers, but could we use this self-learning system to design a lander? The requirement is, this is the mass we want to get in the surface. How could you build the structure as light as possible to reduce mass? And what Autodesk did with their system, they designed this. It's really very organic looking, but we're really looking at other techniques to figure out how to design vehicles to survive in the environments where we want to go. But it's not just us. So Johns Hopkins Applied Physics Laboratory for New Frontiers call actually is designing a helicopter for Titan. Titan is kind of fun. It's got an atmospheric pressure that's 1.5 times, Titan's on Saturn, by the way. The atmospheric pressure is 1.5 times as thick as us. And it's got the mass of the moon. So the gravitational field is 1/6 of Earth gravity, which leads to some pretty fun stuff. So it should be easier to fly in this environment because you have a thick atmosphere and lower gravitational pull. It's about 95 kelvins on the surface. So it's like minus 350 some degrees Fahrenheit. So water is like cement, but you're near the triple point of ethane and methane. So we know that there's a hydrological, let's quote, hydrological cycle on Titan. It's just not water, it's with ethane and methane. So you have an ethane snow that leads to an ethane rain that forms ethane rivers, that has ethane lakes, that goes into ethane oceans. What that means, because the atmosphere is so thick and the gravity is so low, that when it rains on Titan, the drops fall slow. Kind of like the Matrix, a slow kind of rain. But we're talking about launch in 2026 and getting there in 34. Now we're going to get into minor bodies. And what I love about these pictures, you've got the main constituents for minor bodies. You've got comets on the bottom, you've got asteroid on the top, and you'll notice a white dot to the side. That is Gaspra, and it has its own moon. It's only about 1 kilometer across, but asteroids can have their own moons. Now, I just want to give you a sense of the problem. This is a drawing of the solar system out to Mars. Any green dots you see is an asteroid that never comes inside Earth's orbit. If it's a red dot, it's inside of Earth's orbit or crosses Earth's orbit. And you'll notice you don't see any green or red dots because this is from the 1800s. This is before we discovered the first one series. So now I'm going to step you through time just to give you a sense. So if we go from 1800 to 1900, you're now starting to see dots. You see there's some red ones and some green ones. The first I want to give you just truth in advertising. You can't preserve the diameter of the objects and radial distance on the same image. They're just two different scales. So these dots, these asteroids, are not the same size as the planets. With that as a disclaimer, now let's go through the years. So this is how many asteroids we knew in 1900, 1950, 1990, 1999, 2020. We're getting close to 1 million of these objects. Almost 23,000 are near-Earth asteroids, and almost 5,000 are potentially hazardous objects, meaning they could impact the Earth. Now, let me give you an idea of what impacting the Earth means and how scary that is. In 1994, a comet called Shoemaker-Levy 9 got caught in Jupiter's gravity well, and it got pulled into 23 fragments. All 23 smashed into Jupiter. We weren't creative naming it. It was the A fragment, the B, C, all the way to W. The G fragment was the biggest one. It was about a mile across, 1.6 kilometers. Well, our guys in the near-Earth asteroid office, they converted how much energy is released when a 1 mile across object smashed into Jupiter. And they calculated that it was 100 million megatons of TNT. Now, I don't know about you, when I hear million and mega in the same sentence, it doesn't register. I don't know how much that means. So we tried to come up with a way of describing 100 million megatons of TNT, and you can get that amount of energy if you dropped a Hiroshima-sized atomic bomb every second for 11 years. So you do not want to get hit by one of these things. So you can thank the loss of dinosaurs to one of these impacts. That was only maybe about 10 miles across. So we want to study asteroids. So this is Bennu that the mission OSIRIS-REx went to explore and to do a sample return. You can see Bennu is only about, half a kilometer across. And what we did is the vehicle had this long arm, which is right now in the 6 o'clock position below the spacecraft. And what it did is it touched the surface. And as soon as it touched the surface, it opened up these nitrogen bottles, kicking up the regolith and then sucking that material in, which looked like this. So here you can see the foot coming in. It hits the surface and then, and it actually got about a couple of kilograms of material. So it'll be coming back in 2023. We next have a mission to the Trojan asteroids. When you look at a two-body system, there are these things called Lagrange points. There are 5 of them. And in this system, between the Sun and Jupiter, 60 degrees in front and 60 degrees behind are these stable regions called L4 and L5 for Lagrangian point 4 and 5. There are tons of asteroids, which are those green dots in those locations. We're going to visit 7 of these Trojan asteroids on both sides, 7 total. Some, I think it's like 6 on one side, 1 on the other side, just to get an idea of really these, the composition of these asteroids, because this should be some of the most pristine, oldest material in the solar system. But we'll be exploring a number of these things, and we launch this year if things are going on track. There's also, because we're afraid of impacts, there is a technology demonstration called DART, where we have a major asteroid, Didymos, with a little guy called Didymoon, and the DART spacecraft is going to impact it. So it's kind of a kinetic impactor, and we're going to measure how much we deflect it, because we know the mass of the spacecraft, we know its speed, so we know how much momentum it's going to impart on it. And the Europeans may actually have a spacecraft to watch this thing. We also have a mission that we're working on, building right now, called Psyche. Psyche is the 16th known asteroid in the asteroid belt, or I should say discovered asteroid. Asteroids are rocky, and when 2 asteroids hit, they either break into pieces or they stick. If they stick, they now have more gravitational attraction. So other asteroids start falling in and start accreting, getting bigger and bigger. As it gets bigger and bigger, these impacts depositing the heat into the asteroid start to differentiate. Basically, the asteroid is trying to grow up and become a planet. The heat causes the heavy stuff to sink to the middle, so it's trying to make a metal core. The rock floats, and between the rocky floating crust and the iron nickel mantle core, you've got a mantle in between. Psyche, we believe, is a differentiated asteroid where the mantle and the crust have been blown off, exposing just a naked core. So this will be the first mission to a naked core of an asteroid. Final section, the universe. This is why we need different types of telescopes. Here you can see in the second image from the left, this is the Orion constellation in visible light. So you can see Orion's belt, Orion Nebula, Betelgeuse in the upper left-hand corner, Rigel in the bottom right. The infrared image is that same image, but if you had infrared eyes, and you can see that the sword region, the nebula, is really a stellar nursery. It's where you're making stars. The third image from the left is ultraviolet, and the right is X-rays. So basically, different wavelengths gives you different information of really what's going on in that part of the galaxy. Now, this is an old picture, but I just love it. It really just shows you what you can do. This is the Eagle Nebula. It's about 7,000 light years away. The battling design is the field of view of the Hubble Space Telescope. Let's zoom in on that. That's what it looks like. If we now zoom in on the head of one of these things, you can see that you've got these fingers coming out of the top of it. What these fingers are, we believe these nebula, these clouds of gas and dust are forming baby suns. And what happens is, as these suns are forming in this cloud, there's a nearby star where the UV light is evaporating, photodisassociation, the top of this pillar, but it can't evaporate these denser regions. So the region around it is being eaten away, so that the tips of each one of these fingers is a baby sun being eaten out of their solar nebula. So the tip of one of these fingers is about 10 times the size of our solar system. And it's about, I don't know, 7 light years long is one of these pillars. So you're seeing a stellar nursery. Now, again, this is the Hubble Deep Field photo. Here, Hubble was trained on part of the sky for 11.5 days straight. They had thousands of images or points of light in this thing. This is the deep field photo, and you'll notice that this object, and I don't know if you can see it on your monitors, but this actually has a diffraction pattern across on it. Of the thousands of objects in there, there are only 5 with diffraction patterns. 1, 2, 3, 4, 5. Those 5 are 5 of the 200 billion suns in the Milky Way galaxy. Everything else in this picture, you're looking past the Milky Way galaxy at another galaxy of hundreds of billions of sun. And this region of sky is no bigger than a grain of rice held at arm's distance. Do you have any idea how insignificant we are? It's nuts. So this is the first telescope we did to do planet surveying, and what Kepler did, and the reason why I keep this animation here, even though the mission's over, is it does a really good job of watching what happens when an exoplanet passes in front of its star. Okay, so what's going on here is, this is called the transit method. Kepler just looked at one part of the sky and looked for stars that blink. But stars that blink could be because we have an asteroid in our solar system that walks in front of that star. So we look for see things to blink 3 times. If it blinks 3 times, then we're pretty sure it's something associated with that star and not something in our system. But this technique is biased to seeing big things in close orbits. You know, if you have something that has a year that's 10 days long, in 1 month, you'll get 3 transits. But if it's like a Pluto, where it takes 248 years for one, you're never going to see those things. And again, the bigger the object, the easier it is to see these transits. Well, using transits method, we have over 7,000 exoplanets detected. Transits is by far the largest method for doing this, even though there are like 5 different techniques for looking for exoplanets. And based on this data alone, it looks like every star in the Milky Way galaxy should have planets. So you're talking about hundreds of billions of planets in our our galaxy alone. And if you now throw in all the other galaxies, there's tons of them. So what we do is we first detect a planet via some method, could be the transit method. Then we need an independent assessment to say, yes, that object is there, and they're further behind. So they've only done about 4,400 planets that are confirmed of those 7,600. And it's so hard to keep up these numbers because they keep changing all the time. Of those 4,400 confirmed, more than 200 are Earth-sized. And just because you're Earth-sized doesn't mean you have life on it. So there's a difference when people say Earth-sized versus Earth-like. Of those 200, there's at least 30 that are Earth-like, that are in the habitable zone. So there's a lot out there, but the idea of being able to explore those right now, we still have to do remotely. When Kepler died, it was replaced by TESS, which is the Transiting Exoplanet Observer Satellites, and it's just finding hundreds and thousands of these things also. So right now we're trying to figure out what the range is of exoplanets are. We see hot Jupiters. A hot Jupiter, basically think of a gas giant planet that has a year that's days long. So they're really close to their central star and they're just cooking from the temperature. That's why we call them hot Jupiters. We have, think of Jupiters that get kicked out of their solar system, so they're free. They're not bound to a celestial object. They're just wandering through interstellar space. And then based on, if we look at a transit, we can see how quickly the star light dims and how fast it comes back up again. We can get an idea of the diameter of these objects. And because it's a two-body system, we can start to measure mass, which we can start to get density measurements, or volume and the density. We find these things. We find ocean worlds that we believe should have completely encased in water. Now, the problem with looking at exoplanets is the amount of light that comes from the central star versus reflected off an exoplanet is 10 billion to 1. The analogy that I like to use is this is like looking at a lighthouse at night, trying to see a firefly that's an inch away from the light bulb, and you're looking at it from a mile away. And because of zodiacal dust, both the dust in our system and in the exozodiacal dust in the proposed system that we're looking at, you have to do this on a foggy night. So it's a heck of a problem. One idea we're working on now to do this is, it's kind of like building a thumb that you can block the central star with so you can see the objects next to it. We're working on something called a star shade. So you'd have a telescope on the right, to the left is the star shade. We'd do the first deployment, and then we do a second deployment. This thing, depending on the ratio of how far you are from the telescope and the diameter of the star shade, could be 10, 15, 20 meters across, tens of thousands of kilometers away. The star shade would move in front of the exostar, and you'd see the exoplanets in orbit around it directly. So now you can actually start doing composition measurements for those objects. Now, the question people ask is, why are we doing this? And we're doing it basically to find the new Earths, the Terra Novas. Because one of the big questions is really, are we alone? But more fundamentally, why do we do this? It's for 3 reasons. One is to explore the universe, because basically we're curious. By studying the universe, we get a better understanding of our planet. So if we have all these great laws in meteorology and how the Earth's atmosphere moves, and then we go to Neptune and we see that it's got the highest winds in the solar system, we apply our same laws to Neptune and we find they don't really quite work. So now you have to modify our understanding of atmospheric dynamics. Once we modify that dynamics, we go back to the Earth to get a better understanding of how Earth's atmosphere is working. And then you have all the technology droppings. I mean, if you think about someone who was alive in 1921 versus 2021, we have a higher standard of living, we have access to more information, more technology. Where does that come from? I mean, you could close down NASA, but as long as you kept doing exploration and research, your species is fine. The bottom line is space is infinite, so we're not going to run out of things to do. So doing, exploring, and being curious helps our existence. I'd like to close now with a set of images. The one on the left is Earth from low Earth orbit. The middle one is Earthrise, that's Earth as seen from the moon. The image on the right looks boring, but this is taken from the surface of Mars. And if you look inside this circle, hopefully you can see a white dot. That's the Earth as seen from the surface of Mars. And let's go further out. This is a high phase angle of Saturn where you're looking back to the sun. So right now the disk of Saturn is blocking the sun. You could see the rings light up. You see the normal A, B, C, D ring, but you got the F ring and the E ring glowing from the forward sky light. Now this was greatly punched up, but if you look over here in that circle, you'll see another white dot. That's the Earth as seen from Saturn, 1 billion miles out. So I'd like to end with a quote by one of my heroes, Konstantin Edvardovich Tsiolkovsky, one of the fathers of astronautics. He's a Russian. The Earth is the cradle of the mind, but one cannot live in the cradle forever. Thank you.
Are we open to questions?
Absolutely.
I have two for you. First of all, outstanding presentation. I'm thrilled. I'll never forget this presentation. This is Kumar. The two questions I have is, one relates to Mars. I would like you to comment on the Mars dust, because the data that you showed, it looks like Mars dust is not a problem. Second question I have is relates to the universe. Do we have a better idea where this universe came from? Because when I go to talk in elementary schools and high schools, first question they bang me with is, where did this universe come from? And I will be quiet and I will mute my button.
That's okay. I'm going to be able to do a better job with the first and the second question, but let's see. When we talk about Mars dust, since it's devoid of water, you have the same problem on the moon where the dust particles are really very angular because there's, well, at least you have a little bit of erosion on Mars because of the atmospheric pressure and winds. But dust is a serious problem, and we understand, well, we don't understand the mechanics well of the regolith on Mars, because you can see that with two examples. One, we had the mole, which was this thing that was this self-hammering device from the InSight lander that was supposed to go down 5 meters, and it could never get past the initial hole. And we think because of the lack of water there, as this thing was hammering down, the sidewalls just kept breaking down. There was very little cohesiveness, so it had nothing to really push against. So all it did was make the hole wider. And we're seeing that same kind of effect with the first core sample that we got from Perseverance, that we were able to drill into the material, but it was so porous and loose that the integrity of that core sample just turned to dust. So dust is going to be a serious problem, and that's why on Perseverance, we actually landed different materials to see how different materials behave in that dusty environment. And Mars also has these massive global dust storms where a dust storm takes over the whole planet. The whole planet gets encrusted in this, microscopic sized dust particles that just are globally distributed. So I'd say we don't really understand the dust problem well, but we're starting to get an idea of the extent of the problems we have with dust on Mars. But dust is a problem whether you're on the moon or Mars, so it's something you have to solve. As for your question about where the universe came from, you're kind of getting out of my backyard because I'm a planetary guy. We do believe in the Big Bang. All the data really supports 13.8 billion years ago that the universe exploded into existence. But there are a number of really bizarre things that we have to take into account. One is the theoretical physicists, when they're just trying to understand the universe, they find that four-dimensional space-time, length, width, depth, and time, don't really do a good job explaining the universe. You really need 12 dimensions. And my first problem there means there's 8 dimensions. I'm just never going to have a clue to measure because I don't have the sensory input for it. But that led people to speculate that rather than a universe, a one verse, you have a multiverse where you could have had a number of different big bangs, having space time in each of these things that are independent of each other. I don't know how you pass information between verses, but we don't know what triggered a universe to explode into existence. We do know that as the universe expands, things are actually speeding up, moving further and further away from each other. That's what the dark energy is, which we believe is 70% of the known universe. But the implications of that mean that basically all the hydrogen is going to be synthesized into other stuff. So there's going to be no more primordial hydrogen left in the distant future. Stars are going to move further and further away, and their light's going to be Doppler shifted out of the visible. So it means lights from the stars will slowly wink off until the universe dies a cold anthropic death, which then means, did you only have one big bang and this is just going to be the end of it? Or do you have periodic big bangs and many verses? And we just don't know. And it hurts my head. So I'm sorry if that's not really a satisfying answer. Just remember, we're these little slugs, 2/3 the way out on the Carina Cygnus arm of the Milky Way galaxy. Think of us as sentient meat. We have little brains. Think about it, the way we make electricity on this planet, whether it's nuclear or fossil fuel, we boil water to make steam to turn turbines. The number 2 technology is paddles in a stream. So before you think how sophisticated we are, we're kind of that far out of the caves. So we really are a very young species, and we have a lot to learn, both about the nature of the universe and the nature of ourselves, and just how to get along as a species.
Thank you.
You got it. Another question?
Randii, we have a couple questions in the chat. One was from Charles about you were showing orbital asteroids, and so Charles was asking if the positional orbital data on asteroids publicly available. Do you know?
Oh, yeah, it is. There is the Minor Body Center, which is run out of, I forgot which university it was. But if you just do a search on near-Earth asteroids or near-Earth objects, there's an NEO office at JPL, and God, is it Princeton? There's just a Minor Body Center, so you can look up that stuff and you can get orbital information on any of these objects. It's all publicly available.
Okay, and then Sam asked about on an environment like Europa, what kind of instruments you think should be installed on a lander or vehicle that would land in order to confirm with high confidence the presence of any form of life aside from a camera.
We have to be careful there. We are still licking our wounds from Viking in '76, where we brought 3 instruments. 2 were negative, 1 was inconclusive. We have to make a number of assumptions of what life is, and there still is not really a good definition of life. But clearly, you want to bring some sort of spectrometer to understand the composition and looking for heavy organics. You want to find out if you've got if you have different types of carbon, if there's, if it's 50-50 between C12 and C13, or is it just biased one way? Because we know that life has a tendency to have a preference of what carbon it uses. But, you know, when it comes to life, we're just really confused about it. We don't have good definitions of it. You know, when I went to school, the tree of life started with, you know, plants on the bottom that take sunlight and make sugars. Animals eat the plants, animals eat the animals. We go to McDonald's. There it was. And then in 1977, we found by the mid-Atlantic ridge in these hydrothermal vents, we saw organisms living off of hydrogen sulfide. Well, depending on what term you like to use, that's either called chemosynthesis or pyrosynthesis, chemical or heat synthesis. If you're a physicist, energy is energy. Why not acoustic synthesis? Why not magnetosynthesis? You could argue that the early Earth had all these primary producers, all tapping into different energy sources, and the photosynthetic plants were the most efficient at utilizing resources, and they took over the whole tops of the ocean. They crawled out on land, and then when they ran out of space, they tried to go to the bottom of the ocean to go after the pyrosynthetic habitat, but they ran out of sunlight. So what we're going to be doing is we're going to look for an energy gradient that something can live off of in any type. We are going to believe it's using organics, carbons and hydrogens, and our argument for that is we believe life will be water-based because the most common element in the universe is hydrogen, followed by helium, followed by oxygen. Helium is a noble gas, it's inert. So hydrogen and oxygen, the number 1 and number 3 major constituents of the universe, are common. So we believe things will be water soluble. And you can, you have those science fiction people using, let's talk about silicon-based life versus carbon. You can sit there and go, well, yeah, silicon is right under carbon, but as you do nuclear synthesis, you make much more carbon than silicon. So why would life choose something that's rarer when carbon works? So we'd like to believe it'll be carbon-based, but how that carbon is put together, I mean, think of the Earth. There's a big difference between a tree, a sea cucumber, and a cow. But it'll probably utilize whatever energy source is around and just evolve organelles to take advantage of those energy sources. So we're going to look for things that do not move with Brownian motion. See if they react to things, if there's something there. Our bet is there's not going to be multicellular stuff anywhere. It'll probably be single cellular stuff, even though you now could say these ocean worlds, how long were these things ocean? How long were they wet? And could you have evolved multicellular stuff? You could argue just landing next to one of these crevasses that the plume material will eject stuff and it'll fall on the sides of the crevasses that you could then try to analyze. But we do realize if you say on Europa, you're in an intense radiation environment from Jupiter. How long will that stuff exist? Which depends on how much material is there, what kind of material is, what the density is, how much is being expelled. There's just a whole lot of unknowns. But the best thing we're going to do is initially look for composition measurements. And you want to do more than just composition, because I could tell you there's carbon and hydrogen there, but I want to find the amino acids, the fats, the sugars, the other stuff. So it's more than elemental composition. We need to know really what is actually structured there. So you really want to find organics and hopefully big chains. I know that's not as satisfying because we just don't know what we're looking for. But, matter of fact, can I tell you a fun story? You'll love this. We have a group of people at the laboratory that are called astrobiologists. And I go, boy, we haven't found life yet. What are you guys doing? And they go, oh, we do thought experiments. So I said, I'll bite. Give me your best thought experiment. So they'll tell me this story. They'll say, what color are plants? They're green. Why are plants green? Because of chlorophyll. Why does chlorophyll look green? Well, when you hit it with white light, it absorbs the reds and the blues. It doesn't absorb the green. Green bounces off. That's why plants are green. And that's where the biologists stop. The astrobiologists go, why don't plants like green photons? And the hypothesis they came up with is if you're a plant and you're going to do photosynthesis, you have these receptors that absorb photons, but they're wavelength dependent. What color photons would you make first? You can make red photons where there's tons of red photons, but there's low energy per photon. Or you can go with the blues and the purples, which are higher energy photons, but there's less of them. Do you go for quantity or quality? Well, plants got greedy. They did both, and they kept evolving receptors until they had enough to feed them, and then they stopped. They never got to green photons. That's why plants are green. So then they said, okay, now that we know why plants are green, and stick with me here, there's a lot of ifs. If we have a rocky world, and if it has oceans, and if it has plants, and if those plants use chlorophyll, what color would their leaves be if they're orbiting a blue sun rather than a yellow one? And if you go through the analysis, you'll find out that around a blue sun, you know, an O or an A star, all the plants will be orange leaves. And if you go the other way, oh, be a fine girl, kiss me, little baby M star, little red star, the light is so dim, the flux is so low that the plant can't stop. It has to make receptors for everything. So all the light hits it, gets absorbed, so nothing gets reflected off. So plants around a red star would all be black. So these guys are modeling what plants will look like on other worlds before we get there.
Well, it's good to make a hypothesis, and then at least you know what sort of you're looking for. With
That's right.
Yes, with lots of assumptions.
Absolutely.
Mm-hmm.
Yep. Any other questions?
Yeah, I assume all the controls on the robots that you have, they are pre-planned and already because in the system rather than controlling it, right?
Yeah, but there's a problem. If it's pre-planned, it's only what you plan for, and then you have a data bottleneck going from your spacecraft to Earth. And so we're looking at a number of different ideas. We're looking at onboard science data processing so that you would analyze the data on board and just send the information down. Some people are saying, well, gee, let's take this to the logical extreme. Have a spacecraft that has really, really sophisticated data hog instruments that just produce lots of data, put a whole lot of storage on your spacecraft and never send the data down. And then what you do is you just send commands and questions to the vehicle that does the data processing on board and just sends you the answer. Think of cloud computing at Mars. We also want to do autonomous systems where we tell it what we expect and it just sends things that it finds that are different. Whether the science community would trust it or not, that's a different animal. But right now, we're still in the point of view where we send a time-ordered listing of events with time tags that are really choreographed of what we want this vehicle to do as we look for more and more autonomy to impart on these vehicles.
Yeah, it is always a good idea and required that we should have the physical touch of the samples that we have. But again, this adds up lots of logistics in it. So looking at what we have, the smart sensing, smart processing, smart all that, yeah. In situ, I mean, in situation there, can we all do all these various analysis and just get the results to cut down on the other activities, which means moving the samples and bringing and things like that?
Right now, no. And even if we could, I'm not sure the science community would trust us. You know, people have been talking about, hey, why don't we have a global mapper of Mars that we take high resolution images of the whole planet. We can't send that whole data volume down to Earth. And then what we do is have the spacecraft take a second global map and compare at a given location the first image with the nth image and see if there was a change. And if there's no change, ignore it. But if something did change, just send the change down. But I don't know if the science community would trust us because a lot of times, I mean, one of the things we're never surprised about is that we get surprised about something. So how do you get something sent down if we don't know what we're looking for? Yeah, so right now we can't do that, but we are looking towards those kind of techniques slowly and initial capabilities first.
Yeah, because control from a distance with a delay in the transmission is the key issue.
Oh yeah.
And so you can have all those controls in the proper steps with the safeguard for any wrong steps taken and all that. So, you embed all those decisions for the control in the system so that everything goes smooth, and then keep providing that, including of course, the application of the decision process used in the AI.
Yep. It's a problem. We admit it.
Thanks for a great presentation.
Thank you.
I mean, people like me who are professional students, they always like to really learn. Doesn't matter whether I'm retired or not, but yeah, I always learn. I think it's a great thing. And then I think the other thing is the information that people like you who have gathered for years and years. And I think the best thing is really try to pass on to the new generation so that, they don't start from the level 0. They can really pick up and start running with it. I think this is a great, great way. And so Atlanta, I think that's you're doing a great job for AIAA our section and also.
Thank you. And you're absolutely correct, because I think the most important thing you could do as an individual, a nation, or as a species is to learn. And learning is broken up into 2 pieces: research and exploration to get the information, teaching to pass it on. Unfortunately, those are things that the government likes to cut: research and education. But if you think about it, if I have a deserted island, and on one island, people could bring whatever they want, but they can't learn, they'll die out. On the other island, you put people that have nothing, but they can learn, they're going to go to the stars. And the question for all of us is, which island do you want to be on?
That is a great parallel. Thank you. Thank you, Randii.
You got it.
Yes, and I love, as a Russian by birth, and I got education in Russia, I really like your bringing Tsiolkovsky's passage about that the learning cannot stop, and we
That's
have
right.
to continue exploration.
It's him, it's Goddard, and Oberth. Those are the 3 founding fathers of astronautics. That's our profession.
Okay. Yeah, thank you so much. And if there's any other questions, please speak up. Otherwise, I wanted to again express our gratitude for you, Randii, coming here. And by the way, what I didn't mention is that Randii also a member of distinguished lecturers of the AIAA, and the AIAA maintains the distinguished lecturer program and offers to all the sections. And that's how I got to know. That's how I found out about you and offering this talk. And I'm looking forward to our future interactions.
Svetlana, I have a quick go back. Okay. On the Mars dust storm, Randii, I developed a mathematical model, and I've been trying to get some help from MIT and JPL. And so far, I haven't found any help. I can send my work. It's very 3-4 pages of equations, and a couple of guys from Kennedy Space Center, they did the plotting and so on. But would there be a chance that you could help to link me with somebody at JPL who is interested in developing mathematical models for the Mars dust storms? And my overall goal is prediction, not only modeling. How do we predict these dust storms? So I'll send my work to Svetlana. Sure. And I'll appreciate, Randii, if you could link me with appropriate people at JPL.
I will only tell you, I think I can. My only issue is we're still remote, so it's much difficult to do the connections, because I'd walk over to the Mars department and talk to the guys who does the modeling of the dust storms on Mars and get that connection. I can't do that as easily. We thought we were going to open up September 7th, but now with the Delta variant, it's delayed. So it just makes some time, may take some time.
That's fine. That's fine. I have been doing this for almost 10 years now. No
Okay.
problem.
All
I'll
right.
wait.
Okay, send it on.
I'll send it to Svetlana because I don't have your email. So
Okay.
I'll send it to her and hopefully she will pass it on to you.
I will definitely forward. Thank you, Kumar. Yes.
Okay.
And,
Okay.
Zafar, do you have any other questions? Any other questions from the audience? Go ahead.
You know, I am all for dissemination of this knowledge. And so I always arrange for meetings with the different organizations, of course, AIAA, IEEE, AMICO, ACM, and all that. And I think, I'd like to have the opportunity, maybe I'll talk to you, Randii, in case you would like to offer your services
Sure.
as a joint presenter for some of these.
Sure.
And I really believe that, this kind of information, and I want to get involved, get the younger people involved to do that. Some of the pictures that you had, we can pass on to the STEM group,
Yeah.
the kids, the intermediate and lower, the high school kids. They can start looking at, that's the time, that's the type of thing that once they get that and get interested, I'm retired, but when I was giving the presentations, I used to work with the JSC contractors. But when I used to go there, wherever other countries, kids will be so interested in asking about the space. And once they get interested, we find a great scientist when they grow up. So that's basically, I'm all for it. And I might just check with you, see what your thoughts are about this.
Okay.
Thanks a lot again. Okay.
Svetlana, I have a favor to ask of you.
Absolutely.
When everybody gets off, I'd like to talk to you about something. So if there are no more questions.
Okay, well, thank you so much, everyone. We are finishing up, and I'll stay with Randii, and I will stop recording right now.
Thank you.